Okay, I think we're live. I'm looking for confirmation. Yes,
Yeah,
we
let me
are
check and
live
see.
on Twitch.
Ooh.
Ironheart50 says hello.
No confirmation on YouTube yet. But I'm sure it'll happen.
Faces. There's Ian. Oh, I need to open the Patreon stuff.
Oh, there we go. John says, sees us and hears us. So.
Patreon. That was wrong. So kudos on your country having such good elections. You and Australia are both showing how it should be done.
I'm in that the election was posted, everybody went out, voted, the results of the election were accepted by all parties involved, and we're now moving forward. Yeah. Yeah, that's how elections should work.
It has been nice to watch.
Yeah. And it's so quick.
Yeah.
I mean, generally, because our election was announced and then done and wrapped up within about 3 weeks. It was just like very just, you don't have to sort of live in this world where everybody's horse trading and jockeying and
Right.
predicting and polling and arguing. It's just done and over. Moving on. And it's a minority government.
Which you got what you wanted.
Which is my absolute favorite kind of government. It's the one where everybody has to work together or nothing gets done.
Yeah.
And so everybody has to sit down at the bargaining table, that the different parties are able to lean on each other and come together to make laws. And I don't care who wins. I want minority governments. They're my favorites.
That is
yeah.
excellent.
It's too bad you guys can't get that in the US. Like, it's such a healthy way, because you'll get it's so weird. You'll have, like, say you have a liberal minority government, like a centrist minority government, you'll end up with the far left wing and the far right wing collaborating to help push legislation. Or you'll get, like, it's just, everything kind of comes back better to, instead of things just falling cleanly down political lines, you have a much more effort spent on coming up with better legislation. Once you get a majority government, then they steamroll.
Yeah.
And so then you don't get these minority voices having a chance to actually participate in the conversation, which is less optimal. So yeah, I will take a minority government by the party that I would not vote for over a majority government by the party that I would vote for.
And
which sounds bizarre.
No, I get it.
Yeah.
I cannot explain how we ended up in a situation where we're only allowed two parties.
Yeah, you once had, and in fact it was sort of like set up to be that way, but it just never stuck. And so, but it can go too far, places like Italy where there's 30, I don't remember how many parties there are, but there's just like so many little parties, and it's just a mess. And it's really, they spend half of their time just coming up with their coalitions before they can actually get any work done. So that's suboptimal, but there's like a perfect number of parties. We have like 4 parties generally, 5. So we have the conservatives, which are right wing. We have the liberals, which are more centrist. We have the NDP, which is more left wing, and then we have the Green Party, which is kind of left wing, but sometimes has some very right wing policies, but it's very focused on the environment. And then we have the Bloc Québécois, which is focused purely on the needs of Quebec. And so the Bloc Québécois tends to win Quebec, and then. But
does
all
that
those parties
mean
win
the
some
bloc
seats.
of Quebec? Because it sounds like you're saying the blockade of Quebec.
No, it's Bloc Québécois.
Okay.
The Quebec bloc.
Okay,
and so
that makes far more sense.
They used to be a sort of a mix of conservatives and liberals, and then they formed their own party that just focuses on Quebec's needs. And then any party that has to try to win anything needs to bring in the Bloc Québécois to help them get their laws on the books. And so there's going to be this, generally you're going to have to you're gonna have to give Quebec things that it wants in exchange for getting the laws that you want, and that's always kind of interesting as well. So,
I am
okay,
almost done getting the names ready. It's the first week of the month, and I forgot I needed to update names.
yeah.
Sorry.
So I was telling you before, this is the last day of my 7-week sprint post We Need to Talk video, where I
Yeah.
cut off all the ads on Universe Today and gone straight only to Patreon, and it's been it's been a roller coaster. So I've been doing, all of my regular content creation, all of the interviews, as well as doing 10 to 12 interviews with patrons every single day.
Yeah.
And so I've been going from 5 in the morning till 6 at night. So, 13-hour, 14-hour
Yeah.
days every day, go nonstop. And today is the last day. Today I have 4 patron interviews, Astronomy Cast, an interview with a scientist, as well as my live show later on today, plus doing all my regular jobs. And so once that's all done, tomorrow there's nothing in my schedule. The day after that, there's nothing in my schedule. It feels good. Feels
That's
nice.
amazing. That
Yeah,
is
yeah.
absolutely amazing. My lights are still not registering.
It doesn't matter.
Okay.
Doesn't matter.
But
it's so hard.
It's
to-
humorous that both of us had our lights fail. Well, you had
Yeah.
your blinds fail the
Yeah.
same day.
Yeah, my blinds have failed. I can't close my blinds because they ran out of batteries and they don't have a button and they don't work when they're plugged in. So right now my blinds are plugged in and are recharging, but I can't close them while they're plugged in. I could go over and at this point now they've had like 30 minutes of charging. But yeah, this is so stupid.
Yeah, and
So dumb.
my lights are wireless controlled and currently can't be seen on the network.
Yep.
I've hit reset on them. 3 out of my 4 lights are just like, no, we
Yep.
will not. We absolutely will not.
All right, let me know when you're ready to begin.
All right, I am pressing record on the video. I am pressing record on the audio. It looks good. We look good enough given the lights.
All right, ready?
Yeah.
Astronomy Cast, episode 755, Intermediate Mass Black Holes. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. I'm Fraser Cain. I'm the publisher of Universe Today. With me, as always, is Dr. Pamela Gay, a senior scientist for the Planetary Science Institute and the director of CosmoQuest. Hey, Pamela, how you doing?
I am happy to be doing Astronomy Cast.
As opposed to all of the other stuff that's going on right now? Yeah.
Yeah, it's one of these things where we try not to get too political on here.
Yeah.
But what is happening to funding to science in the United States?
Yeah. I mean, for a lot of people who watch Universe Today, and I talk to the people, the fans and stuff, and they're like, "Oh, I really like that you're not very political, Fraser." But that's about I'm gonna have to report on a 25% proposed cut to NASA, cancellation of most of everybody's favorite science missions, the probable cancellation of the Artemis mission, moon plans, the 54% cut to the National Science Foundation. That includes, we don't know what the implications are going to be, but things like, I don't know, Vera Rubin telescope.
Yeah.
There are all these incredible science projects that are in the works, and then you layer on top of that the cuts to the universities. You layer on top of that the cuts to all of the DEI cancellations and cuts that are going on, as well as all of the people to administer this, as well as all the holds and freezes. Science is just going to lock up in the U.S. at this point. That is my objective, non-political take on what's about to happen, and so it could be complicated. And science, NASA specifically, has sort of dodged a whole bunch of bullets that have gone by so far, and now we've seen the budget request. And so we haven't seen what the actual Congress response is going to be, whether they're going to just rubber stamp it or whether they're going to push back and come up with their own version of the budget. So that's sort of the final line of defense.
Yeah. And one of the things that I've realized talking to people is a lot of folks really don't understand how scientists get their salaries and the fact that the vast majority of us are funded entirely through things that can be rooted back to the government.
Yeah.
And this is something that's going to cause a significant proportion of scientists to leave the field entirely.
Yeah. I mean, I'm already talking with people who are saying, I was going to be going to university in the US because it's the best, and now I'm not going to.
Well,
right? So you're going to have this brain drain of people you're going to have this people are going to be avoiding the US science. And then on top of that, people who are already scientists are going to find programs at other universities that are going to give a more stable funding environment. You're going to see large, very established teams of researchers who've been working in, very productive, either fragmenting because of lack of funding or rebuilding their operations in some other other nation like Canada. Like we're unfortunately for the US going to be the inheritors of all of this chaos. We're going to have a lot of incredible researchers are going to come work in Canada because we don't have any of these cuts. So anyway, let's move on. I think this is going to be an episode. Like once the dust has settled and once everything is kind of verified. Like right now, everything is still kind of in the mix. But once everything is verified, I think we'll do an episode which will just sort of say, here's everything that happened and try to give you the most unbiased but brutal reckoning of what has actually happened. So stay tuned for that in some number of weeks or months.
But if you want to find out how scientists are actually paid, go listen to the most recent episode of EVSN at evsn.tv.
Oh, great. There you go. There are stellar mass and supermassive black holes, but very little evidence of anything in between. Where are all the intermediate mass black holes that should be the building blocks of the biggest ones? Actually, the science has been accelerating rapidly, and we now know of hundreds of them. And we will talk about it in a second, but it's time for a break. And we're back. So let's sort of give people a sense of just the gap between them. What is the typical mass of a stellar mass black hole?
So typical mass is a really weird thing to talk about because we are still doing a survey of all the stuff that's out there. Like there weren't confirmed black holes until this century, and we're only 25 years into this century. So we are fairly certain that there's a large number of them that are in the few solar mass to 20-ish solar mass numbers. Then there are more that are bigger. And then there's another gap, and there's more that are even larger. So there's this weird situation where if you have a star that is less than 10 to 20 solar masses, which is a fuzzy number, but mass loss is confusing, it's going to end up becoming a neutron star.
Right.
And create big nebula, big supernova, lots of mass loss. So it ends up tiny, tiny. If you have bigger than that 10 to 20 solar masses, most likely bigger than 20 solar masses, you end up with a supernova going off that creates a black hole in the center, big normal nebula. Life is good. You have an object bigger than 50 to 100 solar masses, most likely 50, and it's going to collapse straight down into a black hole because gravity's like, nope, no supernova for you. But then you get even bigger, and you end up with what's called a pair instability, where as that object tries to collapse, you end up with positrons and electrons getting formed, vast amounts of energy going off. And so you end up with a completely different kind of star go boom and another gap in black hole formation.
Right. So probably a gamma ray burst, right?
Yeah. This is where they're looking at hypernovas and stuff.
Yeah. And because it's all antimatter and matter in the middle, the whole star is just gone.
So you have these two different gaps, and if your star is really big, you don't end up with a black hole. And at the same time, we're finding stuff with LIGO that seems to imply that either they're still forming in those mass gap regions, or things that shouldn't have time to merge have merged. And the universe not matching what we expected will be a theme in this episode.
Yeah. Okay. So those are the stellar mass black holes. And now let's shift to the supermassive black holes. What kind of mass regime do we see with them?
So here we're looking at things that are larger than 100,000 solar masses, and they go up to millions of solar masses.
Billions.
Billions of solar masses.
Yeah.
And so in this case, we're looking at we thought that they probably formed through mergers, but the universe hasn't been around that long. We haven't seen enough merger events. So maybe they form via turbulent infall of matter while galaxies are forming. And then you end up with some mergers that get you to the giant ones, but there's a whole lot of confusion there as well. And we have lost Fraser. Hello?
So then astronomers have always been theorizing that there's got to be something in between. There's got to be something, like, you don't just get these supermassive black holes appearing overnight, that there has to be this accumulation. The small black holes merge with other small black holes. They form larger black holes, and those make bigger black holes. And then you eventually get ones that are in the hundreds of times the mass of the sun, then thousands of times, then tens of thousands, and then hundreds of thousands. And then eventually you move into those millions of times the mass of the sun. So there's like this geometric progression of black holes eating other black holes to walk up that chain until finally you get those supermassive black holes. And the supermassive black holes, they're at the hearts of galaxies, which is sort of like the bottom of the gravity well of the galaxy. And so it's not surprising that they will collect down into the middles of these galaxies and then start to merge up. But we don't see, or haven't traditionally seen, these in-between sizes.
100 to 100,000 solar masses, decided it wanted to be invisible.
Yeah, nowhere to be seen for the entire, essentially the entire history of astronomy. There has been this surprising gap where you would expect to see, like, if you sort of think of a standard distribution curve, there should be lots of the middle sizes and then very few of the biggest ones, the heaviest ones. And yet, in fact, it's like there's lots of the light ones, lots of the big ones, and nothing in between. And that has always been a really big puzzle in astronomy.
And this is where we have to be fair to history and say that prior to the early 2000s, prior to the late 1990s, people were labeling the centers of galaxies monsters. We didn't have this unified idea of active galactic nuclei and Seyfert-1, Seyfert-2s, and quasars all being actively feeding black holes. They literally were just saying, monsters be here. Right. And stellar mass black holes, we didn't have the X-ray and gamma ray data we have today. So we had, like, Cygnus X1, I think is the correct license plate for this one stellar mass object that we said that's probably a black hole. But in the late 1990s, we suddenly started to be able to use the Hubble Space Telescope's spectral capabilities to look in the cores of galaxies, look at the radial velocities of things really close into the core, and say, there, that is so high in velocity that the only way you can explain that is with a supermassive black hole. And we also had Andrea Getz and her team looking at motions in the core of our galaxy and saying, these stars can only be moving like this if there is something that is a supermassive black hole. So supermassive black holes really only started to find in the 1990s. It would take Fermi and Chandra and a whole lot of work confirming things in the radio to figure out stellar mass black holes are actually a thing, and they're kind of everywhere. Yeah. So we're really only looking at 20 years, not even.
All right, we're going to talk about this some more, but it is time for another break. And we're back. So I would say the one of the big revolutions came with the LIGO observatory.
Yes. So with LIGO, we are able to see the release of energy when high mass objects on the small side of what we call high mass decide to merge. So it sounds stupid, but here we're talking about neutron stars. So neutron stars and black holes are the largest stellar remnants. And the sensitivity of LIGO is really just tuned by nature to be seeing the neutron star mergers and stellar mass black hole mergers. And here I have to check my dates. In 2019, May 21st, 2019, there was a merger that caused a wave of space-time that compressed the separation between the mirrors and the LIGO system as it passed through our planet. There was a gravitational wave released that could best be understood as the merger of an 85 solar mass stellar mass black hole and a 65 solar mass stellar mass black hole into a 142 solar mass intermediate black hole. Now, this is a kind of squirrely result because that, 85 solar mass black hole doesn't fit what we expected to exist, and we can't fully explain it except as the merger of two smaller black holes.
Right.
And the universe hasn't been around long enough to justify that. So we're confused.
Right. And that's sort of back to that thing you were saying that that there is no direct mechanism for getting you black holes of that 85 times the solar mass, that you can have lighter ones and you can get maybe heavier ones, but it's that there's that gap where they shouldn't be forming because these stars are expecting to just completely blow up, and yet there is one. And so then you have to say, okay, well, there had to be two smaller black holes that came together to produce that black hole, which is weird because
takes time.
Takes time. Yeah. But there it is. You know, the universe doesn't ask for our permission to show us stuff that are unexpected. So, okay. So then you've got this new tool, LIGO, for being able to detect the collisions, the mergers of black holes, and now it's finding, at this point, almost a black hole merger almost every day.
Yeah.
It's such a productive observatory, and so now we're seeing all of these black holes that are out there. Well, or at least the ones that are merging. We're not seeing all the ones that are out there, the ones that are quiet, that are silently moving through the cosmos, interacting with nobody apart from its gravity. But, don't worry about those. I'm sure it'll be fine. But what about the intermediate mass black holes? We've got one at 125, but that's not 100,000. That's not 200,000. Where are the intermediate mass black holes? Can anybody find them?
Well, so technically anything over 100 is an intermediate mass black hole. Now, globular clusters may offer a solution, and this gets highly controversial because several attempts to say this globular cluster or that globular cluster must have an intermediate mass black hole have been confounded by realizing no, they actually are filled with stellar mass black holes in their core, whose additive mass allows things to get flung around as though there were an intermediate mass black hole. The result that is so far standing up the best is Omega Cen, which is a super weird globular cluster. It appears to have had multiple epochs of star formation. It's
the biggest.
It's the biggest. It's chunky. It's best seen from equatorial regions. So if you live in the extreme north, you're probably not going to see it. It's a gorgeous globular cluster that likes to defy expectations, and because it's a weirdo, people keep looking at it with the Hubble Space Telescope.
Right.
And a team of researchers realized there is data over enough of the history of the Hubble Space Telescope, which is now 35, which really made me feel old to learn.
Don't feel old.
So with many, many, many observations, researchers were able to identify 7 stars in the core of Omega Cen that are moving so fast that they should, unless there's an intermediate mass black hole in there, they should be moving at escape velocities and leaving instead of orbiting in the core.
Right.
Their orbits are consistent with an 8,200 solar mass black hole being in the heart of Omega Cen. So far, no one has been able to disprove these results. This is the one I'm going to go with.
Right. But that is, now we're talking.
Yeah.
That is an intermediate mass black hole. That is something that you couldn't get without mergers upon mergers upon mergers. And of course, in a globular cluster, these are places that are incredibly dense, lots of stars, lots of time for things to find each other, and this is where you would find them. So, and as you said, this is the strongest case, but there have been other examples where it feels like where astronomers say they see almost like the gravitational wake of these intermediate mass black holes moving through globular clusters, distorting the movements of the other stars around them. But obviously, it's a very tricky observation to make, and so they haven't held up as strongly. All right, we're going to talk about the revolution in intermediate mass black hole discovery in a second, but it's time for another break. And we're back. So up until this point, I think, I've been covering this on Universe Today. We've had lots of these like tentative discoveries. Is this some indirect evidence? I don't know. There's, but now the evidence is starting to build.
And this is where we get to the dark energy spectroscopic instrument, DESI. And it is my new favorite thing. Gaia had been my favorite thing. DESI is now my favorite thing.
Yeah. In this brief break between Gaia and Vera Rubin, we get a new favorite thing.
Yeah, and DESI is a instrument that is going through and taking spectra of galaxies in numbers that are ludicrous. They looked at their initial data. This is not the full survey. This is preliminary release. They started with spectra of 410,000 galaxies. They found 115,000 of these were dwarf galaxies. And because they have such high resolution and tiny fiber optics, they're able to resolve smaller things than could be resolved in the past, which means we can start to see and understand smaller things than we could understand in the past. Things that in the past just got blurred out by the stars and things around the cores of galaxies.
Yeah.
And they were able to find that of these 115,000 dwarf galaxies, 2,500 have active galactic nuclei, which is not something we really expected.
Right.
And they also found 300 intermediate mass black holes.
Mini quasars
Yeah.
at the centers of dwarf galaxies that are active. They are feeding and they are blasting out radiation in exactly the same thing that we see with quasars, just at a much smaller level. And so what kinds of masses do we think we're looking at in these dwarf galaxies?
This is the thousands to tens of thousands that
Done.
Yeah, we got there.
Yes.
And what I love is we're now having to figure out, between the data from the James Webb Space Telescope that's like, hey, galaxies formed way before anyone thought. We are now having, because of DESI results, saying here are these intermediate mass black holes everywhere that are actively eating. Because of the LIGO results saying, hey, we have mass gap black holes. We're having to start thinking about things that weren't even the topics of graduate school conversation at the beginning of this century. Things like intermediate mass black holes that maybe came out of primordial, prior to the cosmic microwave background release times. We're having to talk about, well, are these things forming as the galaxies form through turbulence at all
Direct
sizes?
collapse. Yeah. Are we seeing first generation stars being able to be much larger and more massive than anyone thought, producing larger remnants, going straight to intermediate mass black holes? Like, these mysteries are compounding.
And so we're at this really cool point where theorists are going nuts. We're trying to figure out, okay, realistically, what fits the data the best. And we're going to see the extremely broad brushstrokes that we used to explain the bulk of evolution of stars and galaxies in our universe getting radically evolved as we add in new details about things that happened early on, those first stars, what happened prior to the formation of the cosmic microwave background. All of these things caused effects we are finally able to see for the first time. So it's not that we were wrong in the past. Well, in some cases we were wrong. It's that we're now realizing our ideas about the universe were way too limited because, as you said, the universe doesn't ask permission, and it was more creative than we were. And it's really cool.
Yeah. And like, it really feels like we're seeing other examples, like the little red dots that were discovered by James Webb, that the large structures of the universe formed really early on, that mass came together quickly.
Yeah.
And that, as you said, something had to overcome that turbulence in order to be able to bring this material closer together. Because we don't see that happening in stars today. Beyond 100 times the mass of the sun, the outflows of radiation become so strong that no new mass can fall in. Well, how do you get even an intermediate mass black hole with tens of thousands of times the mass of the sun within? Well, how do you get a billion mass black hole within the first 800 million years of the beginning of the universe, right? Like, that's crazy.
Yeah.
Well, so there has to be some kind of direct mechanism that's coming together, that's forcing matter and energy into these small regions and allowing them to turn into black holes on scales that were vastly quicker than anybody had ever thought. And this is the regime that we're now apparently living in. So there's one piece of research, I don't know if you had prepared this, but astronomers have found stars getting ejected on hypervelocity trajectories out of the small Magellanic Cloud, which is our closest example of a dwarf galaxy, and that you can't get this without there being an intermediate mass black hole that's going through three-body interactions, hurling stars at us.
Yeah, and that's one of those results where people are like, let me see if I can come up with something else. So it's one of those results that isn't it absolutely has to be this. It is one of those results where it's like the easiest way to explain this is with an intermediate mass black hole. So yeah, it turns out the Magellanic Clouds fling stars. And one star has been seen moving with a sufficiently high velocity that the easiest way to explain it is you have two stars left behind in a tight binary, and it got flung out in the process. So you probably had an intermediate mass black hole and a binary system, and it got shredded.
Right, tore one of them away, and the other one got a slingshot out of the galaxy. And so it's interesting, the fact that so many of these intermediate quasars, I don't know how you describe them. We need a new term for them. Mini quasars? Anyway.
Yeah, mini quasars.
Mini quasars. These mini quasars have been found at the heart of many dwarf galaxies. Then you can start to make this assumption that in the way we know that there is a supermassive black hole at the heart of every large galaxy, there could very well be an intermediate mass black hole at the heart of every dwarf galaxy.
And this is where dwarf galaxies are super weird, and we are learning you can't actually say every dwarf galaxy regarding anything. There was a point in time where we were like, dwarf galaxies have extremely high light to dark matter ratios, and then we found some that appear to have no dark matter.
Yes. Or stars.
Yeah. Dwarf galaxies are weirdo leftover chunks of stuff and things that yes, some of them appear to have intermediate mass black holes that are actively feeding. Others appear to have had a single epoch of star formation and be, in terms of their stellar population, identical to a globular cluster, but with radically different motions and strange dark matter ratios. They are weird. They're the small leftover bits that apparently do what they feel like.
So this is satisfying, I think, for me, that we are finding at sort of 3 different methodologies that we have available to us now, through gravitational waves, through examining the motions of stars in globular clusters, and through looking at the radiation that's coming from the centers of dwarf galaxies, growing evidence that there are a lot of intermediate mass black holes. And one of the biggest mysteries in astronomy feels like it's now starting to give up its secrets. We're starting to learn the true answer to this question, which is just, it's so great.
Yeah. And it's a really interesting time, because every time we get an increase in computational ability and an increase in telescopic ability, we see these revolutions. The last one was with the Digital Sky Survey. Gaia did a lot for motions and figuring out where things are in stellar populations, but when it comes to galaxies, DESI is that next revolution, and I'm here for it.
Me too. Thanks, Pamela.
Thank you, Fraser, and thank you so much to our patrons. We would not be here without you, because it turns out we need a small herd of people to make us sound good. This week, I would like to thank Astro Bob, Astrosets, Bebop Apocalypse, Bob Zatsky, Brett Mormon, Danny Maglici, David Trogue, Diane Philippon, Dr. Woe, Flower Guy, Frederick Salvo, Galactic President, Scooper Star McScoopsalot, Jeff McDonald, Glenn McDavid, Gold, Gordon Dewis, James Signorovich, Jarvis Earl, Jim Schooler, Jordan Turner, J.P. Sullivan, Just Me and the Cat, Justin Proctor, Christian Golding, Kinsaya Penflenko, Matthew Horstman, Maxim Levitt, Michael Witchman, Nate Detweiler, Old Boomer 847, Paul D. Disney, Peter, Rajevs Akari, Robert Cordova, Robert Hundle, Robert Plasma, Sergio Sansevero, Sersum, Scone, Scott Bieber, Scott Briggs, Sean Matz, Semyon Torfison, Siggy Kemmler, Stephen Veit, Stephen Coffey, The Mysterious Mark, Tricor, Van Ruckman, and Zero Chill. Thank you all so very much.
Thanks, everyone. We'll see you next week.
Bye-bye. And then they saved. Was this 755 or 56?
55.
Okay, I was about to increase the number one too many.
How dare you?
Mistakes get made.
So I just posted my interview with the director of the Vera Rubin.
Oh, cool.
And then there was a spelling mistake in the video, and so we had to take it down, and now we're fixing it. So
that's so stupidly frustrating.
I know. It sucks. It sucks that you can't edit videos in place on YouTube. Like, I understand why they do that, but it's too bad. Yeah. So we're gonna have to put up a new one in a new location and go from there. But the people on Patreon can already see it with the spelling mistake in there, because I can't easily fix that one. And then and so we'll have the YouTube one updated. But it was amazing. Like, it was just, I went right to the head.
They are being so coy, because like they have clearly had first light. They are talking about how they're collecting images on the sky, and they won't tell us when we get to see them, other than June or July.
Yeah, I'm like, how are the pictures? Like, the pictures are great. Thank you. Yeah. When can we see them? You'll see them soon.
Yeah. They have released pictures of people looking at the pictures.
That's just awful, yeah.
The expressions people made seeing the first images, Like, I now want to see the first images too.
Yes,
You
please.
do not need to process them. You can give me the ugly
Yeah, just
images.
give us the raw files. Yeah, give us the FITS files.
And they won't.
And they won't. No, we gotta wait. So, but it won't be long. Like I think we had originally anticipated that there was going to be this big, long commissioning phase, and we wouldn't see stuff out of them until closer to the end of the year with the new operation. But nope, we're probably going to get something fairly soon. So,
They
stay
won't
tuned.
be fully operational for the survey with the complete cadence and data release and everything until later in the year, is what I understand. Yeah.
Yep. Okay, hit us with any questions that you might have. Hal McKinney asks, when stars or larger mass objects get gravitationally flung out at a higher speed than it started with, where does that energy get subtracted from?
So you have the energy of the two binaries here. It's not energy is the way to think of it. Well, I mean, it is
Angular
energy.
momentum?
It's angular
Yeah.
momentum is the way to think of it. You have complete conservation of angular momentum and non-angular momentum. And so what you're having happen is you have this object that's doing its thing. It adds energy as the objects accelerate in. So you have potential energy going to kinetic energy. You have the momentum of these rotations. And during the fling, you are changing the rotation rates and these two, how they're orbiting each other. And that conservation momentum and potential energy going to potential energy from gravity going to kinetic energy is what ends up flinging that additional star.
Yep. Those are all the questions that I see.
Over on Twitter, we have, yay, science from Tunnel Care Bear. And I just appreciate that.
Don't you mean Twitch?
What did I say?
Twitter.
Oh, shoot. Yeah, I did mean Twitch.
Yeah.
What is the fastest flung star on record? I don't know off the top of my head.
About 1% the speed of light, I think. 1,000-ish kilometers per second.
This is me.
So the escape velocity of the Milky Way is 550 kilometers per second. And stars have been seen at close to 1,000.
Record breaker. Fastest star zooms through the Milky Way at 5 million miles per hour. This is a 2023 result.
That's not helpful. 5 million miles per hour.
No, it's not. So that's 2,285 kilometers per second.
There you go. So 2,000 kilometers per second. Yeah. And that is 1%, just shy of 1% the speed of light.
You got there fast.
Shadowcatcher Fox, could these primordial supermassive black holes just be in places in space-time where inflation ended slightly earlier than everywhere else, leaving an area with a higher mass?
So there are various theories that are working on the idea that inflation was something that you have pockets of. Right now, we don't have any observables that say, yes, that is definitely the case. So yeah, that's where we're at with that. Drebsdorf asks, what kind of distribution are we guessing it's going to be? Few large, more medium, a lot of small ones. So I'm assuming this relates to black holes. By far, the majority are going to be stellar mass black holes.
Yeah, it's estimated that there are 100 million stellar mass black holes just in the Milky Way.
Yeah. And so that's because you have so many stars, you end up with so many stellar mass black holes. We're still figuring out the stats of intermediate mass black holes. But you figure galaxies can have hundreds of globular clusters. So you're potentially looking at one supermassive black hole, hundreds of intermediate mass black hole, maybe thousands if you have them floating around in the disks as well. We don't know. And then the millions of stellar mass black holes in a given large galaxy.
Yep.
Scrolling. Existential Squeeze says, I'm so tired. I agree with you. I have had 3 cups of coffee, which is not always a wise choice, but it was a necessary choice.
How McKinney asks, could the perceived mass of black holes be undermeasured because it's a function of the mass of the objects orbiting it, and there aren't enough objects orbiting it yet?
It doesn't work that way. So you have the object in the center uh, is significantly larger than the mass of the objects going around it, and because of that ratio, anything at a given distance from a central black hole, a central star in a solar system, you can have two things of very different mass going around, and they're going to have the same velocity if they're in the same orbit. So this is where you can have the International Space Station orbiting Earth, and you can have an astronaut orbiting Earth, very different masses, and they're both going to have the same velocity if they're the same distance from our planet. So when we're looking at supermassive black holes and seeing the stars moving around them, it doesn't matter what the mass of the star is. What we're probing is the mass of that supermassive black hole that is accelerating everything around it.
Right. I don't see any other questions.
Got a
Any more
rant?
questions? I, I don't have a rant. So we are week 2 of watching Andor, and they've released 6 episodes so far. So they did this with the first series as
Yeah.
well. They're sort of broken up into like a little mini trilogy. So
Chunks.
you have these sort of 3 episode bits that kind of come together. And the last one in the first series was the best part, where they're in the prison and Andy Serkis is the leader of the prisoners,
Yeah.
and it's so good. And so the first 2, they've been great. They've been as good as the first season,
Good.
and so I've been really enjoying them. And it's so rare,
Yeah.
man. Like it's so rare that I'm like excited about things that are coming up in the future. Most of the time, I'm like, oh wow, this thing came. I guess I'll watch it and find out if it's all right. But I'm so excited about Andor, and then the next ones are coming out tomorrow, so I can't wait. That's been good. We've been watching this series on Netflix called Envenaut, and it's pretty good. It's an Argentinian TV show about some kind of weird apocalypse where and they don't explain it. Maybe they never will. I'm not sure. We're not to the end of it yet, but this snow starts to fall, and the snow is poisonous, and so anybody who touches the snow just dies immediately. And so people are trapped inside their houses or buildings and trying to get supplies and go from building to building. They're having to build suits, and so they're very much being like astronauts walking around in Buenos Aires, trying to find each other and stay alive. And it's really good. I'm really enjoying it. So if you're looking for a show like I think there's 6 episodes. Anyway, if you're looking for a show to watch, yeah, it's subtitles, but it's terrific. What else have we been watching? It's about it. Sort of like a weird little lull now in TV. Oh, and The Last of Us. So we've watched episode 4 now of The Last of Us, and that's been great. I mean, it's just so good.
That is cool. I binge read John Scalzi's new book about the moon becoming cheese.
Right, and
It is fabulous. It
oh, good.
was absolutely hilarious. It uses a whole lot of actual science in it. I'm pretty sure I remember seeing that Phil Plait was involved. Scalzi actually is like, don't blame Phil if the science is wrong anywhere in his epilogue. And it just has the most hilarious, taking everything that is ludicrous to its extreme conclusion when it comes to human nature. Like, what extremes will the wealthy go to in order to taste cheese from the moon? So I actually do really highly recommend it. The audiobook is narrated by Will Wheaton.
Yeah,
Always fabulous. Yeah, yeah,
yeah.
I do recommend.
And that would be like vegan,
Uh-huh.
because there wouldn't be a cow that would have created the cheese. So, yeah, I would be into trying cheese from the moon.
Yeah, and it goes into crazy things like what happens when cheese is under vacuum.
Yeah, yeah, yeah. Like it boils off. It freeze dries.
Uh-huh.
It
There's
collapses. It heats up.
consequences.
Yeah, yeah,
It creates
yeah.
its own form of geological activity. So
That's
I really recommend this
cheese
book.
volcanoes. Yeah,
It's
that's amazing. Yeah,
just brilliant.
cryovolcanoes. Yeah, that's fantastic. I got nothing else.
Okay, so Renan Geo says, can you detect the presence of intermediate mass black holes around supermassive black holes, or the supermassive black holes' influence would be so overwhelming? So there's this one really cool result that we didn't get to, where folks were using a radio telescope to study the core of NGC, I think it was 5262. And in the field of view of their radio data was a second radio source that, when they looked at the ratio of brightness and the slope of the energy spectrum, it was actually an intermediate mass black hole. So it turns out one intermediate mass black hole was discovered while studying a supermassive black hole.
Very cool.
Yes.
I wonder if you could like observe the redshift of like the way we perceive pulsars. You know, how pulsars we watch as they're, you know, we can detect an object orbiting a pulsar because the frequency of the wavelengths, or the way we detect
Yeah.
planets orbiting around stars is using the radial velocity method, where you've got the the star moving back and forth because of the tug. And I wonder if you could get this change in in the redshift of a quasar purely based on the gravitational interactions of something that's orbiting around it.
I think the issue would be that it's too smeared out, because you're not looking at the lines of the black hole, you're looking at the lines of the accretion disk, which are already spread due to you have objects coming towards you and moving away from you, and you're sampling a variety of distances. So
Right.
it's already a furry mess.
Zapfan asks, what is the most nearby intermediate mass black hole? Would that be the one in the Omega cluster?
Omega Sen, probably.
Yeah.
I don't know if there's any if none of the ones in other globular clusters actually pan out. Yes, it will be Omega Sen. I don't know if any of the other dwarf
Right.
galaxies would
And
potentially
then,
have one.
right. And then the large Magellanic Cloud would be the next one. And
Yeah.
then, yeah.
Now, so here's the thing to think about. We know from the Sloan Digital Sky Survey and Gaia and everything else that has done this kind of mapping and astrometry that we have eaten many dwarf galaxies. And so the consumption of dwarf galaxies implies the potential for consumed intermediate mass black
Yes.
holes that we
Just
just
roaming.
haven't found.
Yeah. Just roaming around.
Yeah.
Yeah. Yeah, that's always like such a unnerving thought. Like on the one hand, there are 100 million stellar mass black holes wandering aimlessly within the Milky Way. But on the other hand, the orbits of the planets in the solar system haven't been largely changed
Yeah.
throughout the entire history of its, 4.5 billion year history. So if there are flybys of black holes, it doesn't happen very often.
Right. Veronica says, dwarf galaxies, a lovely snack.
Marina R asks, what is the explanation for the simulation made by NASA, what you actually can see when falling into a black hole? I haven't seen the simulation. Do you know what Marina is talking about?
I can only imagine that it's the one that was produced for Interstellar that came out of Robert Hertz's group at JPL. So NASA actually worked with, and Kip Thorne was involved, and so there was a really cool simulation put together for that movie. I'm sure there's been others. That's just the one everyone knows about because it's pretty. What was the question? Sorry.
What was the explanation for the simulation made by NASA? What can actually be seen when falling into a black hole? So I don't like I think people have wondered if you're like someone falling into the, and you don't get spaghettified and you're falling into a black hole, what do you see to the universe around you? Especially what do you see when you cross the event horizon? And you do see things.
Yeah.
You know, you see
light comes in just fine. It just doesn't go away just fine. But the issue is time stops.
Or you see the outside universe start to accelerate.
Yeah.
Yeah, because you're seeing the time dilation.
Yeah.
So and then that causes the light to change, that everything blue shifts. And so everything gets brighter and blue shiftier.
Rewatch the movie Interstellar if you haven't seen it in a while.
I mean that's great for showing it from the outside, but not what it's like to actually fall into it.
Yeah, but it gets across some of the concepts in terms of like how time passes differently for different individuals.
Yeah.
And it's also just really darn good. They recently did a showing of it at the Alamo Draft House that we went to see, and like I had forgotten how good the sound quality and stuff like that is. So, yeah.
Okay, I'm gonna watch this video right now. So there's like that classic Interstellar version, and then you fall. You see everything kind of get distorted, and then you fall across the event horizon, and you see these weird rings appearing and disappearing until you're finally right into the event horizon, and then you just see blackness in front of you.
That doesn't make sense to me.
Yeah. So there's the photon rings. You go past the photon ring, which is the place where light is like moving in a orbit around the black hole. Yeah, I don't think we can explain this video better than. But so here's the video, and you can all watch it. And I don't think we can explain it better than the actual video is.
Can you drop me the link through Slack?
Yeah.
He has YouTube open, I have Twitch open, and we both have Slack open is the way this works.
Yeah. So it's a very weird thing. And they go into like incredible detail showing you all the different lines, all of the bands, until you finally get to the photon ring, and then it gets yeah. The sky shrinks, it gets distorted. It's a very weird video. I can't even describe it. There's a lot of curvy things and things are warping around, and they did this on the supercomputer. So, all right, we've reached the end of our hour. Time to wrap things up. Thank you, everyone, for hanging out with us today here on Astronomy Cast. Thanks in advance to all of the producers and editors who are going to have to deal with our nonsense and turn this into a coherent video.
Thank you to our lighting. No thanks go to my lights or his blinds.
Yep. All right. We will see all of you next week.